Thank you so much for joining us today. My name is Lucia García Duarte, and I'm a data scientist, a spatial data scientist at CARTO. I'm based in Spain, in Madrid. And today I'll show you how can we use spatial data science to analyze climate change risks. So before starting, just for those of you who don't know CARTO yet, I want to give you a very quick intro of what we do at CARTO so that you can better understand why are we here today talking about spatial data science. So basically, in CARTO, we bring together cloud connectivity, visualization, spatial analysis, and development capabilities in a unified workspace, in a unified platform, so that the user can unlock the power of spatial analysis. So basically what we do is to facilitate the tools to exploit geospatial data to get business insights more efficiently and in a very user-friendly way. But now let's move to the topic of today, which is using spatial composites for climate change impact assessment. So the idea here is that I will first explain what are we going to model and how are we going to model it, and then I will go through the data that we are going to use, and later we will get into the details of how are we building these climate risk models to assess the impact of climate change. So, well, as you may know, climate change is a worrying topic these days because of the irreversible impacts that it can have on our planet. So, for instance, in very hot and humid conditions, the human body can no longer cook itself. So the human body starts evaporating sweat to release this heat. But then if this is prolonged during a long period of time, the human body can no longer keep on cooling itself more and more. And this is this becomes more drastic or more important in urban areas where the cooling effect from the vegetation is reduced because there's no plants that give some shadow, and also there's all these roads and buildings, they absorb all this heat and increase the effect of this high temperature and high humidity. So this can have severe consequences for the humans, for the health, and especially for vulnerable population, like the very young population, the children, the elderly, and all these people that is suffering from some kind of chronic diseases and things like that. And this is why it is very important to come up with an appropriate way to model the climate change effects and impacts so that we can mitigate all these risks in the future. And so another thing to keep in mind while working with creating this type of models is that modeling the effects of climate change is a very complicated task because climate change is a very complex and multidimensional and dynamic process that is influenced by many different factors that can be both natural and human factors. And also this is a global phenomenon, so its effects may affect differently these different regions in the Earth. So this is something to consider when modeling. We must know that this is very complicated to achieve. So the idea for today is to show how can we assess the risk associated with climate change, considering these hot and humid conditions for people that is living in urban areas. And we will use spatial composites to do this. I will later explain what these spatial composites are and how can we build them. But for now, it is important that you keep in mind that these spatial composites are very useful and very interesting to use in this type of use cases because they simplify a lot modeling efforts. As I mentioned, modeling the effects of climate change is very complicated. So if we try to come up with an approach that is simple enough to capture all the information that we need, this is definitely the way to go. These spatial composites also allow us to capture spatial heterogeneity, so we can spot differences between different locations, and this is very important because we are able to capture all these spatial dependencies in the data and show this using these spatial composites. And also they are very scalable. We can work with lots of data and the process is quite fast, and also they are very flexible because there are many different ways in which you can derive these spatial composites. Additionally, they facilitate decision making because they're very easy to interpret. You just create the spatial composite, and you can directly visualize it in a map and get some very interesting insights from it. So once we build these spatial composites that we will later see how to do this, we will I will explain a last step in this whole analysis, that is using generative AI tools to create automatic descriptions of these scores, so that we can better understand the data that we have, and we can better understand the results of these scores that we are building. So to begin with, I'm going to go through the different data sources that we used to build the climate risk score. We've considered weather variables and also some socio-demographic, urbanity, and POI related information. As you can see from the map, we've selected two different climate variables that were provided by the Climate Data Factory, which is a company that prepares and processes many different types of climate data. So what we've considered are temperature and relative humidity anomalies that we've computed as the difference between the climatology averages and the projections, the future estimated values. So this is the weather data that we've considered for the analysis, but we've also considered some other variables that are actually derived by CARTO, which include socio-demographic data, which is basically population data. We're considering population at different levels, at different segments. We're considering different segments of the population. We're considering the total population, but we are also taking a look at specific segments, which are the children population and also the elderly population. And in addition to this, we are considering another different type of data, which is the urbanity data. And this is a variable that specifies or categorizes the territory depending on the density of population, the amount of nighttime light, and other variables that have been considered to create this categorization that basically goes from rural and remote areas to medium dense and very high dense locations. And in addition to this, we've also considered POI related information, that is points of interest, that basically consists of counting the amount of points of interest that there exist in an area. And we're considering different types of POIs, like restaurants, transport POIs, leisure POIs, and things like that. So before continuing, I want you to take a closer look at the map. I'm going to go to the next slide to see that. If you see the data that we are using, it's presented in a specific format. We are seeing a grid that covers the whole Earth, and it is made up by cells that have the values of the variables that we are considering. This is a specific way to work with the data. We call this spatial indexes. I don't know if you have heard of these indexes before, but we prefer to use those indexes over working with traditional geometries for a reason. So I'm going to explain why these spatial indexes are optimal to work with spatial data in a much faster way. So the idea here is that spatial indexes are multi-resolution hierarchical grids that are geolocated by a short reference string rather than a complex geometry. What this means is that instead of us working with complex geometries that are very long and they are they occupy more space, what we are doing is working with these spatial indexes that are much simple, that have much simple shapes, and they are also encoded with this reference string that determines which space they occupy in the territory. And a good thing about them is that these strings provide a direct relationship between grid cells at different resolutions, and this is what makes computations to be very, very fast, because the parent cell IDs, so to say, are directly related with the children, and this way we can do very, very fast computations. As you can see in these slides, there are many different ways in which we can present the information using spatial indexes. We have quad-bin cells, we have H3 cells, and we have S2 cells. And there are other types, but these are the most common ones. So from the previous slide, you can see that we are working with quad-bin cells because quad-bins represent the space in squares. So basically what we are doing is subdividing the map, which is in a Mercator projection, into 4 squares. And then each of these 4 squares is being subdivided again into another 4 squares, and each of these 4 squares are subdivided again into another 4 squares, and this is done recursively until we reach a specific resolution. So here our grid is composed by square cells, basically. But there are other types of representations, for example, the H3, which actually was developed by Uber, in which instead of working with squares, we are working with hexagons. The good thing about this type of spatial index is that for a specific cell, all the neighbors that it has are at the same distance to that unique cell, and this makes computations, computing distances like very fast and very easy. But the disadvantage of working with H3 cells is that for a parent cell, if we want to compute or obtain the children cells, we like the 7 hexagons that lie within this parent hexagon do not occupy in space like the same area. Because it doesn't fit like the squares do when you go from a low resolution to a higher resolution. So in this case, when we move between resolutions, we are introducing some kind of distortion here. So there's always this trade-off between data resolution and performance, like having a faster performance. And lastly, we also have S2 spatial indexes, which were developed by Google, and they work with spherical projections. But actually, we tend to use more the quad-bin or the H3 cells than the S2 in this type of analysis. Another interesting thing that needs to be taken into account to better understand why we prefer spatial indexes over geometries is that geometry data is often based on population density. What this means, I will explain it better with an example so that you can better understand. Imagine that we want to represent the amount of POIs that we have in a specific geometry, in a specific geography. If the geography is larger, we would expect the number of POIs to be higher. So when we try to compare or visualize the results in a map, there's some kind of bias that doesn't allow you to understand deeply what is going on. And we usually handle this by normalizing the variable that we want to represent by the density or the amount of population. And this way, the comparisons are more accurate, but still there's some kind of bias there because imagine that there's I don't know, there's a geography that is very large, but the population is very small. Then the comparisons are not exactly or strictly accurate in this case. But however, if we work with spatial indexes, we will be comparing, in this case, the number of POIs that exist within cells that have the same size. So if you take a look at a map with the data, you can clearly understand what's going on, and you can directly understand how the data looks like in space. So this was like a quick introduction. Basically, the things from what I've mentioned, the things that you need to remember are these 4 key points that you can see here in this slide. The first thing is that spatial indexes are smaller to store, they are faster to process, and they are computationally much more efficient than working with geometries. Also, as I've mentioned, running computations with spatial indexes is much faster, so we can combine data sets very easily, and this is very useful to then run your analysis working with the data having it all in the same format. This is a very good way to work with the data to create direct outputs from it. Also, using spatial indexes, we can remove this bias that I was mentioning before that is associated with traditional geographies, and visually it's more impactful, and it's very easy to understand and to interpret using this type of data formats. So now that we know which data we are going to use and how this data has been processed and how this data is presented, I'm going to explain what is the approach that we are going to follow to create this climate risk score. So basically what we are going to do is to create a composite HEV model that is based on composite scores. What is a composite score, for those of you who haven't heard of this before? Basically, a composite score is an indicator that represents aggregated information that defines complex and multidimensional concepts that cannot be measured directly, or that they're very difficult to measure. For example, the risks that are associated with climate change. You do not have any device or any sensor that measures the risk of climate change, but you can measure different different types of other different types of variables that you can then combine to get this one variable that is indicating the risk of climate change. So that's basically the idea behind these composite scores. And as I mentioned, we are going to use this HEV model that basically what it does is, apart from considering the potential danger that we want to measure, the hazard, we are also taking into account the level of exposure, that is the assets that could be affected by the hazard, and also the vulnerability, which is the likelihood of the damage due to the exposure to this hazard. So what this means basically is that when we are trying to model the risk of climate change, we not only need to focus on the hazard that would be this increased or these shifts in mean temperature and mean relative humidity, but we also need to consider which areas are going to be more affected by these changes in temperature and these changes in relative humidity, based on the population that lives there and the assets that could be actually affected by these changes. So knowing that we are going to combine all this information using this HEV model that basically just multiplies the hazard score by the exposure times the vulnerability, we will be able to create this urban at the population level climate score. So how are we going to do this? For each of these subscores, we are going to aggregate different variables that we've mentioned earlier. So for example, for the hazard risk score, we're going to consider two different types of extreme events as potential danger here. We are going to consider the temperature and the relative humidity anomalies that we computed before. Then for the exposure, what we are going to use as a reference for exposed areas are the urban regions and those areas where there's a lot of infrastructure. That is, there's a lot of points of interest there, because this way we are representing not only the places where people live and people stay, but also places that people tend to visit. And apart from that, regarding the vulnerability score, we are going to represent the population that is sensitive to these negative impacts of climate change and the way they can adapt to them. So in this case, we're going to consider not only the total population, but also we are going to focus on these segments of the population that I was mentioning before that may be more affected. For example, the children, they depend a lot on adults. So if there's some like extreme event, they would require an adult to be able to overcome it. So they constitute like a vulnerable segment of the population. And also a similar thing happens for the elderly population. Because of AIDS and some medication that they may be taking, their body may not respond as well as for others to these extreme changes in temperature and in humidity. So this is why considering this as vulnerable population does make sense. So basically the idea here, as you can see from this image, is to create these three different scores and then combine them using the HEV model to create or to derive this final desired climate risk score that represents the risk of the population in urban areas. So to do this, there are many different ways to create composite scores. There are many different methods that you can follow, different ways in which you can aggregate your data, and that depends not only on the data that you have, but it also depends on the knowledge that you have on that input data. So this is what I will explain you in a bit. I will give a bit of an introduction of which methods can we follow and why we should select specific methods over the others, and then I will explain how we computed each of the three subscores that I've just mentioned before. So the first thing that you need to take into account when building composite scores is that you need to know if there exists some kind of like a measurable outcome that is actually correlated with the variables that you've selected to describe the physical phenomenon that you want to model. If this kind of measurable outcome exists, you can then run a supervised algorithm in which you try to create some kind of a regression model to try to explain this measurable outcome in terms of the variables that you already have. But if no such measurement exists, as in our case, because as I explained before, we cannot directly measure climate change impacts, we will go to the unsupervised method, in which we just combine the variables that we have in some way, and we come up with the resulting score. So when we work with unsupervised methods, these are the 3 steps that are usually followed. The first thing that we need to do is to scale the input variables. There are many different ways to do the scaling. We can do a standard scaling, we can normalize the data using the min-max normalization, etc. Then the next step is to weight each of the variables accordingly. So we can give specific weights to some variables and specific weights to other variables. And then the last step is to aggregate all these weighted variables to create this unique, meaningful score. But this selection of scaling, weighting, and aggregation depends again on the data that we have, on the knowledge that we have over this data. So if there is some kind of like expert knowledge, that is the user understands the variables that he's working with and knows which ones could be more relevant for the analysis and for deriving or modeling the phenomenon that they're working with, then he would be able to scale the variable, scale the variables, selecting the method that he thinks is more appropriate, and he would be able to say, okay, this variable is more important than this other variable, so I will give a weight of 0.6 to this variable and a weight of 0.4 to this other variable, and then he would, the user would select how he wants to aggregate the data, for example, using a normal weighted average. But on the other hand, if we do not have this kind of knowledge, we don't know which variables are more important because we are not sure, or maybe because of due to the nature of the variables, you may not know like if one variable should be more important than others, or if both should be equally important. So in this way, we go and use some other types of methods that are automatic methods that try to maximize the variance of the data. What this means is that these methods try to assign larger weights to those variables that have a high variance, that is, those variables that have more information. So more informative variables would be more important when it comes to deriving and building our final score in this way. And again, there are different ways to do this, and that depends on the data that we have. If we have, for example, not so large data set, we would go for the entropy method. In this entropy method, basically what it does, entropy measures amount of information. So what we're going to do is to relate the amount of information, which is the entropy, to the weights, so that we can assign greater weights to those variables that have a greater entropy. So what we do is to standardize the variable first, and then we compute the proportion of the values of each of the variables. And with this proportion, we are able to compute the entropy following the formula that you have in the slide, which is it's not so important to understand like the whole concept. The whole concept, like the basic idea, is that with this formula we're getting the entropy, which represents amount of information, and this is going to be used to create or to derive the weights that we will be giving to each of the variables to later aggregate them. And another option that we could follow in case our data is much larger, and for example, we do not have any outliers in the data, is deriving or running a principal component analysis. For those of you who don't know or are not familiar with principal component analysis, basically this is a dimensionality reduction algorithm that is used to transform your variables into a different set of variables, and both sets of variables contain like the same amount of information but expressed in a different way, so that you can go to your projected space and only keep those variables that have most of the information. So basically the idea is that we are projecting our variables into a different space. Our variables are correlated, and we are projecting them into a space in which the variables are uncorrelated. And these uncorrelated variables represent follow like the direction of maximum variance. This means that if we select the first component that we derive from this from running this PCA, this principal component analysis, we will get the variable that has the majority or the most amount of information, so to say. So just the idea here is that we are combining our variables into a different space, so that we can get unique variable or score that contains most of the information that we had in our original data set. That's basically the idea behind this algorithm. So there are more methods that can be implemented, but these are the ones that are most commonly used and most important. So now that you have kind of like an idea of what can be done, I'm going to explain exactly how we selected the different methods depending on the subscore that we wanted to create. So for example, for the hazard score, we used first PCA because we wanted to maximize the variation of the input data. The first thing that you need to know is that we computed this score globally. So we took all of the data that we had, all of the temperature and relative humidity anomalies data, and then we computed we ran the analysis and computed the first PCA, because weather data is a global phenomenon, so it does make sense to consider all this data together. So since we are working with a lot of data, and also these variables are correlated because weather variables are usually correlated, and also we cannot specify which of these two variables is more important than the other, then going for the first principal component is the best option here in this case. Another important thing to mention here is that when you run a PCA algorithm, the first principal component can have a positive direction, can have a positive direction or a negative direction. It's kind of like arbitrary because of the way in which you compute it. So one thing that we do is to correlate one of the variables to this score, to this first principal component, so that we can better understand what this principal component means. Just for you to understand this better, what we've done in this case is to correlate the first principal component, the score that we got, with the temperature anomaly. In this way, we know that for higher temperatures, the risk of climate change should be higher. So if we correlated directly the temperature with the first score, we know that for higher values of the score, the risk would be higher in this case. So this is just a way to better interpret the results and to know what they mean. And another thing that we've done also for interpretability was to normalize the resulting score between 0 and 1, so that 0 means no risk and 1 means maximum risk. And then we go to the next subscore, which is the exposure. Actually, the exposure and the vulnerability scores were computed in a very similar way. For both of them, we used custom weights because we wanted to specify some importance to different variables, and we wanted to change the way in which we wanted to aggregate them and scale them. And also, we computed this country by country. So if you remember, the hazard score was computed globally, but here for the exposure and the vulnerability, we did this country by country. Why we decided to go this way? Because we wanted to account for the inter-country variations in socio-demographic and infrastructure patterns. This means that it does not make sense to create a population score globally, because countries with extremely high population will take over the score. And then we wouldn't be able to see differences between cities that lie within a country that has a low population. So this is why we thought it would be more interesting to derive these two types of scores using this country by country approach rather than following the global one. So in this case, for the exposure risk, as you can see from the slide, we are giving equal importance to both the infrastructure and the urbanity, because we are not specifying any weights. So basically, we want to say that both variables have the same importance. They have the same weights when it comes to computing the exposure score. If you take a look, in this case, the scaling function that we've selected is the ranking one, which basically what it does is to compute a percent rank. And we selected this scaling function because we are considering an ordinal variable, which is the urbanity. And when working with the ordinal variables, this method is recommended because it retains the ordinality component of our ordinal variable. So this is why we selected the ranking one in this case. And lastly, we specified the linear aggregation function, which is basically a weighted average. And in this case, we specified this because using this linear approach, high values in one variable are compensated for low values in other variables. So this means that if we have a variable that has a high value and a variable that has a low value, it doesn't matter exactly which one of the two variables is higher. It will account for exposure, exposure risk either way. So this is what it means, that some high values do compensate for low values in other variables. And lastly, for the vulnerability risk, again, we used this country by country approach, specifying some weights. In this case, we actually give more importance to some variables than to others. For example, as you can see, we gave a weight of 0.2 to the total population, but then the remaining 0.8 was split into the other two variables, which are the children population and the elderly population. So we are actually given more importance to these segments of the population than to the overall population in each location. So the most vulnerable population segments will have greater influence over the final score, basically. And here, as you can see, we are specifying a different scaling function. We are selecting here the min-max scaler. Actually, there's not a standard for this. We could have also selected used a standard scaling, for example. This is more like a trial and error thing in which you need to try different approaches and see which one works best with the data that you have. But in this case, we did select the aggregation type geometric, in which we are doing geometric aggregation, in which it's also some kind of weighted average, but in this case, high values in one variable won't be fully compensated with low values in others. So this is a less compensatory approach. And also like the balance between the input variables is important. So if we have two variables with the same or similar values, this will be more rewarded in the final score, so to say. And another important thing to mention here is that the geometric approach only works with strictly positive values. So we needed to remove from the analysis those areas in which the population was 0. And also another important thing that I forgot to mention is that you can see for the vulnerability and also the exposure, there are some blank or dark areas, like black areas, in which we did not compute the scores. And this we did not compute the scores here because these are areas that are remote or that are rural, and we are focusing only on urban areas. So this is why we're not covering like the whole area. But for example, for the hazard risk, even though we are not considering the whole, we are only focusing on urban areas, we want to consider like the whole territory, because as I mentioned before, this is a global phenomenon, and it makes sense to consider like the data that we have in the whole globe, in the whole territory. So now that we have the three subscores computed, it's time to combine all of them to create our final climate risk score that basically represents the risk of hot and humid conditions for urban populated locations. So as I explained before, following the HEV approach, what we're going to do is to multiply the normalized hazard score times the normalized sum of the exposure and the vulnerability, as you can see in this slide here. And then what we are going to do is to normalize the resulting index to have it between 0 and 1, as I explained earlier for the hazard score. And once we have this, we can just bucketize or discretize the continuous score into a set of groups. In this case, we are dividing the score into a set of 5 equal groups. So there are groups of equal length, and that would go from very low risk to a very high risk. And to do this, we are using this BigQuery function that is ML bucketize, in which we're just taking the risk and then assigning to each of the values of the risk a score, a group. So for example, in this case, we are generating 5 different levels. So if we go, so the locations that would have a very low risk would be those that have a risk between 0 and 0.2. And then a low risk would be assigned to locations that have a risk between 0.2 and 0.4, and so on. So we have these 5 final groups. So this is how the computation works. I want to show you now the results that we got. So let me just move to the map so that we can navigate through it a bit. As you can see in this map, we have on one side the climate risk at the urbanity level, and on the other side we have the hazard score. But we could also visualize the exposure, and also we could take a look at the vulnerability, just to get more insights and better understand what's going on. But the main understandings that we got from the analysis is that the areas that are more at risk are those areas that are highly populated and, for example, like big city centers, but those areas that also have like a high hazard score associated to them. For example, you can see in this area that we have a high hazard. There are some more red locations which represent very high risk than in surrounding areas where there is not such a huge risk coming from the temperature and the relative humidity anomalies. And also, it's not only interesting to take a look at these conclusions, but we could also go a bit deeper. And let me just zoom out. My connection is not very good, so it may take a bit to load. But if we take a look at this map on the right, sorry. Hold on a second. This should be going faster, actually. Yeah, we can see, for example, that here, even though we have not computed the climate score, because these are places where there's no population living there, the hazard score, the hazard risk is very high. So this would suggest that maybe in the future this ice that is over here would melt, and this will rise the sea level, which will actually have some effect on areas in the proximity. So we not only need to focus on the results of the climate score, but we also need to take a look at all the subscores, because all of them can provide some meaningful information. And that is all for the creating the scored part. I want to go now to the part in which we generate these automatic descriptions. So as you can see, we've included here an additional level in the map that if we go to it, we can see a pop-up that appears that defines basically what each risk group represents. So I want to go back to the presentation to better explain to you how we did this. Basically, what we did was to use Google Cloud's generative AI capabilities to run generative AI model that provides descriptions for each risk level that we've computed before. So we would have 5 different descriptions, one for each risk level, from very low to very high. And we did this using this workflow that we developed. Actually, this workflow, we created it using CARTO workflows, which is our low-code data preparation tool and analysis tool. So this is shown like this for just to better understand how it looks, because we have all these blocks that makes the description much more simpler. So basically, the idea here, let me just go to the workflows, is that so that we can better see which information does this contain. I don't know why it is not working. Okay, we have it. So basically, the idea here is that we have some input data that basically corresponds to the different variables that we have. So actually here it is loading. Yeah, we can see that we have all the different cells, the quad bin cells that I was talking about before, with the total population, the total number of POIs, and also we have the different scores that we've built. And we have also a dictionary that includes each variable and a description of it. So we will input these two tables to this component here. And this component, what it does is to take this table here and compute some summary statistics of the data. It computes the statistics like overall and also for each of the 5 groups that we have. And then it creates a prompt that is fed to the generative AI model, which is actually a Google model that is called Palm 2, which is a large language model. And this model outputs the 5 different levels. And to create this prompt that is generated, it considers a task description that we need to give to the component, and also the summary statistics that we've built, and the description of each of the variables. And with all this information, it creates the final labels. So if I go back to here, I can show you what the task would look like. Actually, this is not the whole task. This is some like the beginning of the task. Actually, apart from this, we need to include what I mentioned before about the summary statistics and also the description of the variables. But the thing to highlight here is that we need to specify in very detail what we want the model to output, because if not, it's not going to work. So we need to define what the input table contains, how the score was obtained, and describe in detail what we want the algorithm to define to us. And this is the output that we would get. Each of the boxes contains the label that is given to each of the scores, from very low here in dark gray, in dark green to very high. And I am actually the results sometimes are more accurate, sometimes are not so good. But the important thing to mention here is that these models are actually very being improved every day, and in the near future we will for sure have very detailed descriptions of the scores that we can use in the analysis of the climate score. So for example, here you can see that for the very high score, we are getting a description that says that this group is characterized by a very high hazard, high exposure, high vulnerability, because there's a large predicted increase in temperature and relative humidity, and there's very dense areas over there, and there's a lot of vulnerable population, like the very young and the elderly. So it kind of gets the idea of what it needs to output. So basically that's all for the presentation of today. I wanted to give you some key takeaways for you to summarize what we've been discussing. So the first thing is that to effectively create these climate risk models, we need to have the appropriate tools, the appropriate data, and also like accurate data, but accurate data in the appropriate format. So if we want, for example, as we were mentioning before, to reduce processing efforts, using spatial indexes is a good way to go, because they are very, very fast. Also, as we've seen, creating this modeling, these risk models is very complicated. So if we are able to simplify the approach and create these spatial composites, summarizing all the information, just to visualize it directly, this is a very accurate way to combine all the information to be able to interpret the results in an easy way. And as we've seen, we are able to use these HEV models that allows us not only to consider the hazard score, but also to take into account the exposed areas and the areas with that are more vulnerable. And lastly, as we've seen, we can use these generative AI tools to make the score more understandable and to facilitate interpretation to the map reader. So that's all on my side. Thank you so much for listening. So if you have any questions, I will be happy to answer them. You can also contact me by LinkedIn if you have any remaining questions.